Having learned the fact that only certain specific components of voltage and current contribute to the transfer of finite average power or energy, it will be good to understand the idea of power factor. Let us consider a sinusoidal voltage source V of t connected to a circuit which is inside an equipment, and this equipment draws some current I of t, and the waveforms of voltage and current V of t and I of t are shown here. The waveform of voltage V of t is shown in blue color, and the waveform of current I of t is shown in red color, and both of them are varying sinusoidally. Vm is the peak value of the voltage and Im is the peak value of the current, and phi is the angle between the zero crossings of voltage and current waveform as indicated here. And how does the power waveform look like? The power waveform, the instantaneous power waveform, also looks like a sinusoid because it is a product of voltage and current, and voltage and current both are sinusoidal, and the power waveform is shown in green color. We know that the average value of this power PAV is equal to Vm Im by 2 cos phi. It can also be derived mathematically by integrating this waveform over one period. Let us try to take a closer look at the current waveform. So I of t can be expressed as Im sin omega t minus phi, and if we expand this sin omega t minus phi, we get two terms, cos phi sin omega t minus sin phi cos omega t. Now if we observe the voltage and current expressions, the voltage is given as Vm sin omega t, and current has two components. One is Im cos phi sin omega t minus Im sin phi cos omega t. In the previous lecture we have seen that the component of current which has the same frequency as that of voltage and in phase with voltage can only contribute to average power transfer. And which is the component of current that is in phase with voltage here? The first component, Im cos phi into sin omega t. So that is why Vm sin omega t and the first component of current, Im cos phi sin omega t, underlined here, together contribute to the average power. How about the second component of current, Im sin phi cos omega t? If you multiply the second component of current with the voltage, that means Vm sin omega t multiplied by Im sin phi cos omega t, this will result in a function with zero average value. That means it does not contribute to any net power transfer. That means it does not contribute to any useful work done. So the power that contributes to useful work done is denoted by P work here, which is nothing but the average power. P average is given by Vm Im by 2 cos phi. It can also be written as Vm by root 2 times Im by root 2 cos phi, and Vm by root 2 is nothing but the RMS value of the input voltage Vrms, and the second part Im by root 2 cos phi is the RMS value of the current component which is responsible for useful work done. So that we are denoting by IRMS work. And what is the total RMS value of current? Total RMS value of current denoted by IRMS is simply Im by root 2, as we know. If we observe, the RMS value of current which is needed to do useful work is only a fraction of the total RMS current drawn, and that fraction is cos phi. That means though we need only Im by root 2 cos phi current to do useful work, we need to make sure that the source and the connecting cables to this equipment can actually withstand more current, that is Im by root 2. Why? What do we mean by withstanding current? When current flows through any physical element, due to the resistance of the physical element, there will be power loss, and that power loss will be dissipated as heat, and that will cause temperature rise, and that temperature rise should be within specified limit. For example, if you consider the source to be a transformer, the secondary winding of the transformer carries this total RMS current, and also we have some cables running from transformer all the way to this equipment, and all these cables actually carry this total RMS current Im by root 2. That means even though to do useful work our equipment needs only a fraction of current Im by root 2 cos phi, we should rate our equipment, or we should select the transformer and the intermediate cables in such a way that they can carry a full current Im by root 2 and operate safely. That is why this total RMS current IRMS is referred to as I rating here. So if we need to calculate the power rating of the input side equipment, we should multiply voltage and current Vrms into IRMS, the total RMS. For example, if we are choosing a transformer to be on the input side, the power rating of the transformer is calculated as Vrms into IRMS. So P rating is equal to Vrms into IRMS, and that is known as apparent power PAPP. Power factor is a way to look at these two powers in a relative manner. Which two powers? P work and P rating. The power corresponding to the useful work done and the power corresponding to the rating of the source that needs to be selected. If I need to select a source of power rating exactly same as that needed to do useful work with my equipment, then my equipment's power factor is unity. When I have an equipment with poor power factor, that means I need to choose a source of power rating more than the power I need to do useful work. The power factor cannot be more than 1 for obvious reasons. Even though P work and P rating, or P average and P apparent, are the same physical quantity power, which is the product of voltage and current, two different units are used for the average power and apparent power. The average power is typically expressed in watts and the apparent power is expressed in volt amperes. So the expression for power factor in this case is IRMS work divided by IRMS rating, and that turns out to be cos phi. And what is phi? Phi is the phase angle between voltage and current. So the cosine of phase angle between voltage and current gives the power factor when the voltage and current both are varying sinusoidally. What happens when our equipment starts drawing non-sinusoidal currents? Because we know that in power electronic circuits the currents are not necessarily sinusoidal. Let us consider this example where this particular equipment or circuit is drawing a current. It's an alternating current, but it's varying like a square wave. The peak value of the square wave is Im, and it has the same frequency as that of the voltage. The voltage is still sinusoidal, having a peak value Vm. Now if you look at the product of voltage and current, the power, which is shown in green color, it has again the frequency which is twice that of voltage and current, but it is definitely not sinusoidal. Of course it is periodic, and it has some average value, and that is the average power that is getting transferred to this circuit. Let us see how do you arrive at this average value. Let us take a look at the composition of the current waveform. The voltage is anyway purely sinusoidal. If you take a look at the current waveform, it has many frequency components, and these frequency components can be found by Fourier series. So the Fourier series expansion of I of t, the current waveform, is given here, which is 4 Im by pi into cos phi sin omega t minus sin phi cos omega t plus 1 by 3 times cos 3 phi sin 3 omega t minus sin 3 phi cos 3 omega t plus 1 by 5 times cos 5 phi sin 5 omega t minus sin 5 phi cos 5 omega t plus so on. Now let us take a look at the frequency components which contribute to average power. We know that the component of current which is having the same frequency as that of the voltage and in phase with the voltage can only contribute to average power. So it's again only one component of the current, which is the sin omega t component of the current, which can produce the average power here. So the average power is basically the average of the product of the first term in I of t and V of t. So that is 4 Vm Im by pi into cos phi into sin square omega t, and the average value of sin square omega t is half. So the power corresponding to the useful work done, or the average power, can be expressed as 4 Vm Im by 2 pi cos phi. Now if we decompose this 2 in denominator into root 2 and root 2, so Vm by root 2 corresponds to Vrms, and the remaining current 4 Im by root 2 pi cos phi is the RMS value of current that corresponds to the useful work done. However, since all the components contribute to the total RMS current which has to be supplied by the source, the input side equipment or the source has to be rated for IRMS total, and the total IRMS is simply Im because it's a square wave. So the power corresponding to the rating of source, which is the apparent power P APP, is equal to Vrms into IRMS, and the power factor is again the ratio of P work to P rating or P average to P apparent, which is given by 2 root 2 by pi times cos phi. P average is expressed in watts and P apparent is expressed in volt ampere as discussed earlier. So this again translates to IRMS work divided by IRMS rating here, as Vrms is present both in the numerator and denominator. So if you look at numerator, the numerator is IRMS work. The IRMS work is expressed as 4 Im by root 2 pi cos phi. And what is 4 Im by root 2 pi? We know that 4 Im by pi is the peak value of the fundamental component of this square wave, which has a maximum value of Im. So 4 Im by root 2 pi will be the RMS value of the fundamental component of the current. The fundamental component of current is shown in dotted line here along with the current waveform. So the RMS value of the fundamental component, that is I1 RMS, is 4 Im by root 2 pi. And the denominator is anyway Im, which is the total RMS value. So the power factor in this case, when the voltage is sinusoidal but the current is non-sinusoidal, can be expressed as I1 RMS divided by IRMS multiplied by cos phi, and we have already defined this I1 RMS by IRMS for AC waveforms, which is the distortion factor. So IDF1 is equal to I1 RMS divided by IRMS. So with that definition, the power factor becomes the product of IDF1 multiplied by DPF. What is DPF? DPF is the displacement power factor. So the displacement power factor is cos phi, and what is cos phi? The cosine of the phase angle between voltage V of t and the fundamental component of current I1 of t. So when we have a non-sinusoidal current that is being drawn from a sinusoidal source, the angle between the voltage and the fundamental component of current waveform is going to give us a part of the total power factor, which is known as the displacement power factor. The total power factor in this case is the product of displacement power factor and the distortion factor of current. Let us now consider a more generic case where a non-sinusoidal voltage source is present and a non-sinusoidal current is drawn from that source. So the voltage source is again a square wave voltage source with maximum value Vm, and a square wave current is drawn from that voltage source which has a maximum value of Im, but the square wave current is phase shifted by phi, an angle phi with respect to the voltage, square wave voltage. So the square wave voltage can be expressed in terms of its constituent harmonic components using Fourier series. So that is shown here. V of t is equal to sigma n is equal to 135 4 Vm by n pi sin n omega t. We know that 4 Vm by pi is the peak value of fundamental component of a square wave, and any other harmonic component has 1 by nth of the magnitude of the fundamental component. And similarly, I of t can also be expressed as sum of harmonic components. It is equal to sigma n is equal to 135 and so on, 4 Im by n pi multiplied by sin n omega t cos n phi minus cos n omega t sin n phi. Now if we take a look at the voltage and current components, there are many components. Ideally there are infinite components of voltage and current that come together to contribute to average power and do useful work. So the power corresponding to useful work, P work, which is equal to P average, is expressed as sigma n is equal to 135 and so on, Vm Im by 2 into 4 by n pi the whole square cos n phi. So it's an infinite series, and it may be a little tedious to evaluate this infinite series. Alternatively, the average power can be directly found from the power waveform itself. So if you plot the power waveform, the product of voltage and current, it looks like another kind of square waveform, but of course with non-zero average value. So the P average is 1 by pi integral 0 to pi P of t d omega t, because the periodicity of P of t, the green waveform, is only half of that of the voltage waveform or current waveform, or the frequency is twice. So with this integral we can easily determine the average value of power. P average is equal to Vm Im into 1 minus 2 phi by pi. And how about the rating of the source? The source rating is given by the apparent power, which is Vrms into Irms. That is simply Vm times Im in this case. So the power factor in this case, where the voltage is non-sinusoidal and also the current is non-sinusoidal, is given by, again, the average power by apparent power, which will be 1 minus 2 phi by